We're now looking at the overdetermined problem specifically. Now, what exactly do we mean by the overdetermined problem? Well, again, we're going to be looking at a minimization problem that's like this. We've kind of saw this minimization problem when we looked at the projection theorem. But instead of having y and m, now we have ax and b. So it's a similar problem, it's subtle differences. So again, this minimization problem is non-trivial if b is not in the range of a. If b is in the range of a, then that means there's some x that will make this norm 0, and we're done. So this kind of a problem is often associated with least squares problems, curve fitting problems like what we saw before. In the event that b is not in the range of a, no exact solution exists. That does not mean this linear algebra problem is meaningless. It just means that we can't get an exact solution. We look for a least squares type solution. So again, we have our projection theorem. In this case, instead of having y as our vector, now b is our vector. Y now is this vector instead of m star. And we're looking at, in this case, m is the range of a. Okay, so b, the vector b, is not in the range of a. And so we're looking for the x that minimizes this. Alternately, we can think of minimizing y in the subspace and b not in the subspace. Okay, so this actually looks like what we saw in the projection theorem. But if we think of y as being equal to ax, then we have the same problem as we saw in the projection theorem. And with the projection theorem, we actually worked through and we saw the solution. The solution we can think of in terms of a point solution, that is for a specific value of b, there is some x star that solves this problem. Or we can think of it in terms of a solution map. That is a formula for obtaining a minimizer for any b. So x would be, for example, some matrix times b. That minimizes this norm. So how do we find the point solution? How do we find the solution map? So again, for a point solution, the point solution is such that the norm of ax minus b squared must be greater than or equal to the norm of ax star minus b squared. So for all x, I need to have this for x star to be the point solution, the minimizer. So we're going to let delta be x minus x star. So if we take the difference in norms between ax minus b and ax star minus b, and we can go through and do a version of FOIL and show that this difference in norms can be written as the norm of a delta, so a delta is equal to x minus x star, and there would be a fourth term over here, but that would be the norm of b minus b. Okay, and since that's 0, then we are good with that. So this condition should say that all of this quantity is greater than or equal to 0, but we have these inner products in the middle that kind of like muddy the waters a little bit. So we need to understand what's going on with these inner products in the middle. Okay, so if we look at that inner product in the middle, so there are two of them. One has the ax star on this side, then a delta, and then this is just the other way around. So here we just look at it this way. So this inner product we can show is equal to this inner product. That is, I can take the a over to the other side, and it becomes a adjoint over here. And so this quantity gives us something called the normal equation. The normal equation says that this quantity is equal to 0. And so the theorem that establishes the solution for the overdetermined case requires the normal equation to be satisfied. And we're going to show that a solution to the normal equation exists. Well, it's easy to show that a solution to the normal equation exists, even if an exact solution to this equation does not exist. So we know that since b is not in the range of a, we cannot get a value for 0 here. But what the normal equation says is we don't need something that is 0 here. We just need it so that when I multiply by a adjoint, I get 0. Okay, that's a different problem. So here is the statement of the theorem for the overdetermined case. Again, the proofs are reserved for a separate video. So you can go and look at the proofs in a separate video. So here, Theorem 1. The vector x star is a solution to this problem, this minimization problem, minimum over x of ax minus b norm squared, where b is not in the range of a. Okay? X star is a solution to this problem if, and only if, it satisfies the normal equation. So if there is a vector that's x that satisfies this normal equation, then it is the solution to this minimization problem. If there is an x that solves this minimization problem, then it automatically satisfies the normal equation. So that's what the if and only if. There are two sides to that theorem. Okay? So clearly the normal equation is important. Clearly the normal equation. And actually, you can actually rederive this problem, this constrained minimization problem. You could actually rewrite it in terms of a calculus problem where you take the first derivative, set it equal to 0, and blah, 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 all that kind of stuff. So, and again, the normal equation pops out. We won't take that approach, but that is an approach that can be taken. So the normal equation, again, is an important equation. What is the normal equation telling us? Well, here's a vector. That vector times this matrix is 0. That means this vector is in the null space of A adjoint. Okay, so that's an important thing. So this gives us a solution, the point solution to the minimization problem. What about the solution map? Well, the solution map says this. The matrix B is a solution map if and only if it satisfies this equation, which is similar to the normal equation. The difference between this equation and this equation, obviously, is instead of having x star, we have b, and instead of having little b, we have an identity matrix. So notice that this basically takes it out of being dependent upon a specific vector b and puts it in terms of the general case of the identity matrix. So the matrix is a solution map if and only if this equation. So this is the solution map version of the normal equation. So summarizing the overdetermined problem, we have that this minimization problem leads to the normal equation. The minimizer, we can go through and show, is equal to a pseudo-inverse times b, where we actually haven't really talked much about the pseudo-inverse. We'll talk about that later. But this is the minimizer. The solution map, x star, is equal to b times b, where b is a matrix that satisfies this normal equation. In this case, there is a unique minimizer. In this case, there is not a unique solution map. So this is a solution. This is the overdetermined problem. Again, we're trying to find a solution to the problem ax minus b. There is not an exact solution, so this gives us the best in this least square sense. That is, we're minimizing the norm, the sum of the squares of the elements of the error, and we get a solution, a minimizing solution. So this is the overdetermined problem.